Okay. All right, then are we good to start? Let's get started. So I'll be going through chapters 4 and 9 today because both are relating to waves. So the plan is we'll go through chapter 4 first and then into chapter 9 with a break in between. So could everyone please mute? That would be helpful. All right. D over dy and the one at the end, sorry, I can't say that. Could you please mute? Okay, so let's get started. So on waves, the first part, oscillations. So oscillation refers to any kind of back and forth motion by an object or any kind of repeating motion. Like an example would be in pendulums on a grandfather clock, you know, the big clocks with a huge swinging thing down. So whenever we're describing oscillatory motion, there are three main words that we make use of. They are period, frequency, and amplitude. So now let's go into each one of them. So period is the time taken to complete a full oscillation. So if we take an example of a pendulum, let's take a pendulum which is swinging that way, and then back and forth because it's an oscillatory motion. So when I say one period, it's essentially the path that it takes in order to return back to the same position. So if we're talking about here and I refer to this point as the starting position, it's when the pendulum goes here, back here, and then back to the same spot again. That is one complete oscillation, and the period is how much time it takes in order to do that. Now, frequency. Frequency refers to the number of oscillations per period, and it's pretty much just 1 over the period. So like let's say I have this pendulum over here, it takes 3 seconds to complete a full oscillation, then its frequency, so the period, let's say is 3 seconds, then its frequency is going to be just 1 over that. So it's going to be 1 over 3 seconds minus 1, or as the SI unit dictates, it should be hertz. All right, then next we have amplitude. Amplitude is the maximum displacement from the equilibrium position. So now back to this pendulum over here. The amplitude of this pendulum is going to be the distance from here, the equilibrium position, to when it's over here, because that's the maximum this pendulum ever travels. That distance over here is the amplitude, and it's given by the symbol A. So now the oscillatory motion that's quite often looked at in this course and in exams in general is simple harmonic motion. So now there are three main conditions you need to know for any object that's going through, that is the three conditions required for any object to be in simple, to say that it's in simple harmonic motion. So these are the three conditions. The first one is the period and amplitude is always constant, meaning that every single time this pendulum oscillates, it will always reach the same maximum displacement, and it will take the same amount of time to complete the full oscillation. Which means in this pendulum will always go till here. at max. It'll never cross it, it'll never go behind it, like it'll never come over here, nor will it ever come over here. It will always reach till here, and it will always take 3 seconds to complete this. That's the first condition for anything that's undergoing simple harmonic motion. The second is that the period is independent of amplitude, which means no matter what the period is, no matter what the amplitude is, the period will always be the same. So even if I, like, all of a sudden change this string's length, let's say this is a ball and string pendulum. If I make the string longer, now it's, let's say, like this, then its period will still be 3 seconds. If it's going through simple harmonic motion. The third one is the displacement, velocity, and acceleration can be represented using a sine or cosine function when they're plotted against time. What I mean to say is, if I now create a graph out of this, with, let's take displacement to start off with, which is usually given by the symbol x. And in the x-axis we have t as in time. The displacement from the equilibrium point will always can be represented using a sine or a cos function. It doesn't necessarily have to be like x equals to sine t. It doesn't have to be always exactly like this. It can be something like x equals to 3 sine t over 2 plus pi over 7, for examples. So it doesn't have to be only a sine, but it must be represented by some kind of a repeating function like sine or cos. And there's also one more, well, it's not really a condition, but you can use it when describing simple harmonic motion, that is, the acceleration or the force experienced by the string will always be towards the center. This is the restoring force, the force acting backwards, which means it's always going to be in the opposite direction of the displacement, and it is also proportional to the displacement. Because the restoring force is proportional to the displacement and mass is a constant, you can also say that x is proportional to minus a, where x is the displacement and a is the acceleration. Alright, and that's simple harmonic motion. Now, there's also the concept of phase difference and coherence. So now let's get into that. So coherence refers to the waves from a source that are of same wavelength and frequency, but doesn't necessarily have to have the same, and has the same period. Which means only if they share all of these, they can be considered to be coherent. So an example of this, you would have heard, of course, a coherent light source. A light source that's giving out a single colored light. That would be called a coherent light source because all the light waves coming out of it are of the same frequency, wavelength, and period. Now we have the concept of phase difference. Now I'll add in a picture over here for phase difference in the notes. I think I forgot to do that, so I'll draw it out. So there's, in some cases, if you let's say plot out the displacement and time graph of two waves, because remember first we said earlier, if they're going through simple harmonic motion, they'll be given by a sine function or a cosine function. So let's just draw a sine wave to represent the displacement of a certain object going through simple harmonic motion, or SHM, its displacement from the equilibrium point at various points of time. Now, let's say there's another object going through something similar, but except its displacement varies a bit. Now, if you see, both of them have the same amplitude, which is, I'll just mark the amplitude over here, which is generally given by xo. Then both of them have the same wavelength as well. Oh, sorry, that's not the wavelength. It's actually wavelength over 2. Yep, that's more like the wavelength. Now both of them have the same wavelength, yet their displacement time graph doesn't seem to match. So in this case, we say that both of them have a phase difference. And now energy in simple harmonic motion. So at all displacement values, like at any point during a simple harmonic motion, the total energy in the object that's going through simple harmonic motion will always be the same. You need to keep that in mind, it's really important. Now, the total energy will always be the sum of the potential energy and kinetic energy. Now, to visually show this, let's go back to our ball and pendulum case. It doesn't have to be just in a ball and string pendulum. It can also be in a mass spring pendulum. So now at this point, let's say that this is time equals to 0. And we also say displacement equals 0 because it's at the equilibrium point right now. Over here, at this point, the velocity of this pendulum is maximum. Thus, it's at maximum kinetic energy. And its potential energy will be at its lowest value. So I'll just write it down as E K is max and E P is minimum or just min. Now as the ball goes all the way up here, and as we said earlier, the force is constantly acting backwards and it gets stronger as we go out here, and eventually over here it stops, which means over here, let's just put it as time equals to 1 second, just as an example. And we know displacement is now maximum. And over here the pendulum has come to a complete standstill, which means the velocity of the pendulum here is 0. That means automatically the kinetic energy over here will be at its minimum, or just 0. And as it goes up here, it gains more potential energy because now it's higher up. So the potential energy is maximum. And can be written as 0. All this kinetic energy now got converted into potential energy. Thus, the total energy still remains the same. So that means ET, or the total energy of the object going through simple harmonic motion, is equal to the sum of the kinetic energy, EK, plus EP. Yep. And that's it for 4.1. Before I proceed, just let's see if we're all doing good. Yep, the Google Doc will be shared once I've done my sessions. You'll have access to all of them. So are we good to continue? I'll put the link up over here and I'll make sure to pin it. It should be up by the end of this week, I'd say, by Friday or so. All right. Then let's go ahead to 4.2 traveling waves. So now what is a wave? A wave is a disturbance which transfers energy and momentum from one place to another. Now, when we're describing waves, in addition to time period, frequency, and amplitude, there are other words that we can use in order to describe a wave. They are crest, the highest point a wave will ever reach, or the maximum positive displacement. Then trough, the lowest point a wave ever reached. Let me just change that a bit. Yeah, that's more accurate. Maximum negative displacement, and wavelength, the distance between two consecutive troughs or crests, or the length of a complete oscillation. So now let's represent this all out in a diagram to make things a bit more clearer. So once again, we have time and displacement, and we have our wave over here. Yep, sorry, that's not really consistent. I think I should draw it a bit better. Yep. All right. So now, as we said, maximum positive displacement would be the crest, which means this point here is the crest, or the equivalent over here to the amplitude, because that is the maximum positive displacement. Now, the maximum negative displacement, or the trough, would be over here, which would be xo, and because it's in the negative axis, so minus xo. Now the wavelength will be the length from here, one crest, to here, another crest. This is the wavelength. Okay. Now we have two types of waves. They are transverse waves and longitudinal waves. So now transverse waves are waves where the displacement occurs at right angles to the direction of energy transfer. So like this, we can say the energy is going this way, and it's going up and down towards this way. An example of this would be light waves, if that's one. And another one would be like, if you ever have been at a pool and let's say a ball fell over there. So let's just put a pool over here. And then your ball's fallen over there. Quite often we just try to push water over here and it forms something like this, hoping that the ball will eventually reach over here so that we can pick it up. Now that's another example of a transverse wave, because the displacement is up and down, but the direction of energy transfer is that way. Now next we have longitudinal waves. This is where the displacement occurs in the same direction as the energy transfer. An example of this is sound waves. So what I mean to say in this case, what we have is, let's say we have a bunch of air particles. There are going to be regions where they all compress together. Let's just draw some really quickly. And then regions where they are a bit more spread out. Sort of like that. So they keep going. So these air molecules, the particles come closer together and then stretch further apart, and then come closer together and then once again stretch further apart. that would be a longitudinal wave. Quite often in sound waves, when they just pass through air, that's the kind of motion they take. Now, all waves except for electromagnetic waves, which are transverse waves, require a medium to travel through. So, electromagnetic waves are the only ones that do not require a medium to travel through, which is the only reason we get sunlight. Because if you think about it, between the Earth and the sun, it's a vacuum. There's nothing over there. The transverse waves can just simply go through the vacuum and come to us. Now, wave speed. Wave speed is the distance covered by a wave per unit time. So it's essentially how fast the wave is going. So we can use the method of speed as we learned in chapter 2, which is distance over time. And you can also make use of another formula over here, which is v equals to frequency times wavelength. Velocity equals frequency times wavelength. Now, to really show that this ends up in velocity, let's take a look into it, because we have v equals to f wavelength. So now we know wavelength is the literal length of the wave, how long the wave is, which means this is given in the unit meters. And frequency is given in hertz. Or, because frequency is 1 over period, it's the same as per second. So meters times per second gives us meters per second, which is the unit for velocity. Yes, and you need to remember, for all electromagnetic waves in a vacuum, their speed is 3 times 10 to the 8 meters per second, which we also know as the speed of light. Now we've entered 4.3. Before that, any questions? Yep, other transverse waves other than electromagnetic waves do require a medium to travel through. Like, as I gave you the example of when you push water in a pool, you have transverse waves forming over there and they require a medium to travel. In this case, it's the water itself. Alright then, let's go ahead to 4.3 now. Wave characteristics. So the first thing is our wavefronts and rays. So wavefront is a surface through the crest and normal to the energy of propagation. So what it is essentially is that if I have a wave like this, this here would be a wavefront because it's perpendicular to the direction of energy transfer, which is this way, and it's a surface through the crest and it's normal to the energy transfer. So that would be called a wavefront. And an array is something that's normal to the wavefront and in the exact same direction of energy propagation. So this would be array. I've never really seen them ask anything directly about wavefronts and rays, but it's something you should know and can help you understand other things, especially in chapter 9. That's when it becomes really heavy. Now we have wave intensity. So like I said earlier, waves are a disturbance that transfers energy. Because it transfers energy, it must also transfer power, because power is just energy transferred over time. So now we know that intensity is always given by the formula power over area. So it is P, as in the power transferred, over 4 pi x squared. I'm not sure if you can see that, so I'll just write it out over here. We have P, intensity I equals to P, the power transferred, over the area, 4 pi r squared. Why is it 4 pi r squared? Because we're assuming that the wave starts at a point source like this, and it spreads out all around in a sphere. And as we know, the surface area of a sphere can be given by 4 pi r squared. Okay. Now, and also there's one more thing you should remember. The intensity of a wave is proportional to the amplitude of the wave squared at any given point. This relationship always stands true. Quite often you have to make use of this in questions. There was one I saw a few days back that used it. So please do keep this in mind, and I'm pretty sure it's given in the data booklet. Alright, and in this case I wrote r, though we usually refer it to be x because we're talking about the displacement over here. So x squared. Alright, now the principle of superposition. So what superposition says that if two waves arrive at a given point of time, at a given point at any time, they will form a wave with an amplitude equal to the sum of the amplitude of both waves. So what I mean to say is that if we have a wave coming in like this, and then we have another wave. This is like, let's say on a string, you've just pushed it up and down and formed a wave. And these two waves are heading towards each other. When they interact with each other, you form one big wave like this at that point where they hit each other, where let's say the amplitude of this is x and this one is y, then this will be x plus y. That's what the superposition of waves is. And note, if the amplitude of one is, let's say, like this, and the other one is like this, and let's say this is x, and this is y, the amplitude of this is y, then the resultant wave, as it will be a sum of this, and this actually has negative displacement with respect to x, this will actually be x minus y. The displacement of this wave will be x minus y. So just to make sure before I go into polarization and Malus's law, just let me make sure if you're all good, is which one in the data booklet? The intensity equation, I believe so. Let me just check it quickly. Nope, that isn't given in the data booklet, but they've given you that intensity is proportional to the inverse of the distance from the source squared, or displacement squared. So you don't really have to remember it, but it would be helpful if you did. So I'll go ahead and start on with electromagnetic waves and polarization now. Let's go back to the notes. Yeah. So electromagnetic waves, when they travel, they generally propagate in all planes normal to the direction of energy transfer. What I mean by this, like let's say a wave is traveling like this. In that case, the wave will be propagating like this. It will also be propagating like this, and at many other angles. I can't really draw 3D graphs on this, but I hope you can visualize that. Or let me just try and I'll put up a picture on the notes as well to make this a bit more clearer. So now plane polarized waves. Now these are referring to the waves that propagate in only one plane, meaning if it's traveling like this, it'll only be propagating like this. You don't have anything in the side that's going like this, or anything that's perpendicular to this but still in the same direction of energy transfer. Nope, it'll only be in one plane. So when we're talking about electromagnetic waves, there's a reason why they are called electromagnetic waves. It's because when they propagate, they have two fields around it. Let me try and do it visually. There are two main fields that propagate while it is propagating. So you have one field that's like this, and you have one field. Let me try and make it look like it's perpendicular to this but not in the same plane, but still going in the same energy transfer direction, something like that. So one of them, like let's pick this one, is the magnetic field. I'll just label it as MF, and this one will be the electric field, or the EF. So electromagnetic waves, that's why they are called electromagnetic waves. You have a propagating magnetic field on it and a propagating electric field on it. Both of them have displacement that's perpendicular to the direction of energy transfer, and they are also perpendicular to each other. So they move in the same direction, but they're perpendicular to each other. Now you have things called polarizers that can effectively remove these planes of. So a way to visualize a polarizer would be, let's say this sheet over here, or a block that's opaque and can't let any kind of light or waves to pass through, and there's a slit over here. So now if you have, let's say, a string going over here, going through this, sort of like that, and now if you do start shaking the string so it goes like this, it'll continue to go through because the slit allows it. But now if I change things a bit, now if I shake the string a bit differently, if I make it go sideways now instead of going up and down with the same slit for the string, make it go like this, it will no longer be able to pass through because the slit blocks it. This hole can't allow the sideways motion of the string. That is essentially what a polarizer does. It blocks out all planes of light except for one. While this may be like a really big example of a polarizer because I have a huge opening over here and then I have a string that's passing through, but in actuality, they're really small. These slits that I showed you, they're actually really small, and they come on, like, let's say a glass, and they're all over. You can't really see them, but that's how they function. Now whenever you polarize light, it will lose intensity, and Malus's law describes the intensity of any light that has been polarized. So Malus's law states that the intensity of the wave that has passed through Malus's law states that the intensity of the wave. Sorry, who's unmuted? Could you please mute? Towhead 19. Yep, thank you. So Malus's law states that for any wave that passes through a polarizer, its intensity after passing through the polarizer equals to the intensity before entering the polarizer squared times the cosine of its initial angle of polarization squared. What I mean to say is that if we have, let's say, a polarizer over here, and it's sort of those grid lines or those slits as I told you about going in this way, right? And then if I have a wave that's passing through, that's going somewhat like this, not in the exact same direction, but such that if we put it flat against the polarizer, it comes out like this, then you must take its angle to the polarizer. This angle would be theta, and if its intensity is IO, then the intensity of the wave that passes out, which will look like this, it will be parallel to these grid lines over here. That intensity I will equal to IO squared cos squared theta. That is Malus's law, and it is given in your data booklet. And note, Malus's law applies only if the light that's passing through the polarizer was polarized before it entered, which means it must be in a single plane before it actually enters the polarizer. If it's a plane of if it's unpolarized light, if it's not polarized on any plane, then the intensity after passing through the polarizer will be 50% of its original intensity. That's because, if you remember when I said earlier that light has electromagnetic field, it has an electric field and a magnetic field that's propagating and they're both perpendicular to each other. So what essentially happens is when it first passes through the polarizer, one of those two fields gets blocked out by the polarizer, leaving the other. So therefore the intensity just gets halved. So with that, we're done with 4.3. Let me just check if you're all good before I continue to 4.4. Maybe a few yeses in the chat will do. Or if there are any questions, please do ask. With how the resultant wave is parallel to the polarizer, how does that work? Because the initial wave is going. Oh, so if the initial wave is parallel, I mean its direction of propagation is parallel to the polarizer, then it'll simply pass through. There'll be no effect on it. Because in that case, the angle to the polarizer, because remember, if we have a polarizer like this and we have these like this, if the wave falls exactly on this plane, then its angle will be 0 degrees. And the cos of 0 is 1, so the intensity after polarization will pretty much be equal to that squared. Just give me a moment. Oh, I see. I think I've made an error. Right, it's not squared. I apologize for that. It's just the intensity times the cos squared. I may have mistyped that. Yep. So basically with the vertical. Yep, alright, yep. Well then, let's go on to 4.4, which is wave behavior. So now first let's look into reflection. So when a wave is reflected, the angle of incidence theta I will be equal to the angle of reflection, theta r. Note, when I say angle of reflection and angle of incidence, it's not the angle to this. So you need to draw a normal out first. Let's say this is a mirror and you have light that's coming down like this. It'll reflect out like that. This angle here will be theta I, or the angle of incidence, and this angle here will be theta r, which is angle of reflection. And these two are equal to each other. They will always be equal to each other as long as the surface is even and it's flat. If it's not, then you could have some weird reflection patterns. Now, refraction. Refraction is another property of waves. So what essentially happens is, because waves travel through different mediums, and they actually travel at different speeds in different mediums, this can cause the wave to bend as it enters the medium. So let me try and show you exactly why it bends. So I've told you that waves will bend when they pass into a different medium. So let me put that out. Let's say this is air, above here is air, and we have water over here. And let's look into light waves, because we know for a fact that light travels slower in water than in air. So let's look into it. So we have a light wave, let's say it's coming down like this, right? Now, when it comes into contact with water, we know that in water, the light moves slower, which means over here, because it's moving slower, it'll actually become like this. You can imagine it by, if you have two things going at different speeds and if you attach a rope between them, you'll notice they start tilting. That's essentially what happens over here. These begin to tilt and it passes through water in a different angle. I hope that looks clear. Maybe I should make it look a bit more clear. Sort of like that. Yep. So it's coming in like that and it's going like that. So it bends inwards because it moves slower in water. That's what happens over here. And you can use Snell's law, which I've written out over here, in order to describe this bending. So we have n, which we call as the refractive index of a certain medium. The refractive index is pretty much the ratio of the speed of light in that medium against the speed of light in the other medium, actually. So if we want to talk about, let's say, the refractive index of water, then that will be equal to the speed of light in whatever medium it's coming from. Let's just say it's air in this case, and the speed of light in water. That's the refractive index of water with respect to air, or if you want me to do it with respect to a vacuum, I need to put the refractive index of the vacuum. This relationship shows the refractive index of any medium. Now, to relate that to the angle of incidence and angle of refraction, this will be equal to sine theta air, or the angle at which it was in air was a sine, before it got refracted, and sine theta water, which is the angle after refraction. So this is Snell's law relating the refraction of light in different mediums through the speed and the angle at which they interact. When I say theta air or theta water, when I say air, let's say the wave is coming through the air like that, and then into water. It bends inwards because it's slower in water. Remember, when we take angle of incidence and angle of refraction, we always take the angle to the normal. So that's going to be theta air, or theta I because it's the angle of incidence, and that's the angle of refraction, or theta water. Yep. And that is Snell's law. Then you also have total internal reflection. Now, total internal reflection, it refers to the cases in refraction where what happens is the angle at which it strikes a medium is so large that it doesn't pass through to the other medium anymore. It'll either like go along the plane like this, or it might reflect in like this, and so on. This is known as total internal reflection. Now, the angle at which it goes right parallel through the plane is known as the critical angle, or theta c. Now, note, total internal reflection only occurs if the speed of the wave or the speed of light in that medium is slower than the medium it's going to transition into. So like this only works if this is water and this is air. Things like that, where the speed is faster in the medium it's going into as compared to the medium it is coming from. And if you want to calculate the refractive index of any medium with respect to a vacuum, you make use of a similar equation as I showed you earlier. So now let's say if I want to do the refractive index of air, I do the speed of light c over the speed of light in air. There's a difference between the speed of light in air and in a vacuum, but it doesn't have to be in air. This can be water, and this would be the speed of light in water. That's how you get the refractive index for any medium, for light per se. Now we have diffraction. So we went through the two wave behaviors already. That's reflection, when it hits an object and just goes straight back, and refraction, when the light seems to bend or move at different speeds when it enters different mediums. Now we have diffraction, which is when it passes through a slit, it starts spreading outwards. So if you have a wave coming in like that, when it goes through the slit, it starts spreading outwards. So what happens is when the wave interacts with the slit, let's say like this, the light actually bends and goes outwards like this and keeps spreading outwards, becoming larger and larger. Yep, and also the greater the hole or the slit size, the larger the diffraction effect that will occur. Now here's one type of diffraction that you really need to know for chapter 4. It's double source interference. Well, it doesn't always have to link with diffraction. You can also just talk about two sources, but let's put it in terms of diffraction. So now let's say we have two slits like this. And we have a coherent light source that's giving light out like that. And we place a screen over here to see what happens to the light. So now over here, this diffracts outwards, on and on. Same from this slit, getting bigger and bigger until they all interact over here. Now the interesting thing is when they interact over here, you actually see a pattern. You see a pattern of bright and dark spots. So you have, let's say, a bright spot over here. I'm putting the bright spots out like this. And the bright spots start getting weaker as you go further away from the center. And this here is called the central maximum. So there's a reason for why this occurs. If you remember, we had the principle of superposition, which we mentioned earlier. So what's happening in this case? You have a wave array that's coming here, from this slit. And you have another one that's coming here. These two waves arrive over here. And now note, both of them have covered the same distance from the slit, and they are both coherent, meaning they have the same wavelength, period, frequency, and amplitude. And now, when they interact over here, they actually superimpose, and because they have the same phase difference, they constructively interfere. So constructive interference occurs when the path difference or the phase difference is n lambda. Lambda is the wavelength, n is any whole number. What happens over here is, in constructive interference, the amplitude of the resultant wave over here is 2a if a is the amplitude, because of which you have a bright spot, a maximum intensity at this stage. Because if you remember, we said intensity was proportional to amplitude square, which means if amplitude is maximum, then the intensity is maximum. And then over here, at this dull spot, we have something called destructive interference occurring. Over here, we have a path difference of n equals to 1 over 2 lambda, which results in the wave cancelling itself out. So now to show you visually what happens. So let's say we have this wave over here. Okay. I'll just put it in a graph so that we can make a bit more sense out of it. That is the displacement, and that is the time. So let's take the crest over here, xo. Now if we have a path difference of half a wavelength, or something of a similar degree like that, n plus 1 over 2 lambda, where n is a whole number, so n can be 0, so half a wavelength, we will end up at this point, which is minus xo. Now note, by the principle of superposition, when two waves interact at a certain point at a given time, the resultant wave will be a sum of the two amplitudes, which means over here the resultant wave will have an amplitude of xo minus xo, which equals 0. So you have a dark spot over there. There's no amplitude, there's no wave over there, so therefore the intensity at that point is 0. But now if we have a path difference of 1 lambda, a whole wavelength, you end up at another crest. And by the principle of superposition, which once again means that the resultant wave will be having the sum of the two amplitudes, the amplitude of the resultant wave would be 2xo, which is the maximum amplitude that you'll ever have. So that's why you have a bright spot over there. That is what happens in double slit interference or double source interference. They work in the same way, as long as the two light sources are coherent. So now an equation that will help you in double slit interference. Now let's once again get the drawing of a double slit out. We have the light source shining light onto the two slits, and we have a screen over here. Let's say we have a bright spot over here, 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 bright spot over here. So now the fringe spacing, which is the distance between two maxima, two consecutive dark or light spots, S, will be equal to, S will be equal to the wavelength of the light that's coming through, times D, the big D, which is the distance between the screen and the slit, over small d, which is the slit width. That is the equation for any double source interference or a double slit interference. Now, any questions before I move on? Let's see. Sorry to ask. If the polarizer is not in the same plane as the light, as in the wave is traveling from the left to right, but the polarizer is on the same plane, then the polarizer is useless. Well, if it's in the same plane of light, the polarizer is useless. The angle will be 0, therefore the resultant intensity will be the same. So it just simply passes through. So in a way, you're right, it is useless. Any other question? In refraction, if V changes, how does lambda and frequency change? Well, frequency is always going to be constant. The frequency of the wave will be constant. And sorry, let's put out the equation. V equals to F times wavelength. So now we have velocity that decreases. Sorry, I'll change my statement. What happens is the wavelength of the wave, or lambda, will remain constant while the frequency will decrease when it refracts. Because, wait a second, I think I might be getting something wrong. Just give me a minute. Y squared, I'll get back to you on that. I actually need to check that again. Is there any other question? Well, I'll just move ahead. Now the last part, standing waves. So standing waves. So when two waves of the same speed, wavelength, and amplitude move toward each other, a standing wave is formed. Now the crest and the shape of the wave will remain the exact same even as a standing wave. Now in this case, the crest and the troughs are known as antinodes, where the region where displacement is zero is known as a node. So what I mean to say is, if we have a standing wave on a string, something like this, it's constantly oscillating up and down, so it also goes through this position. So now this region here where there's no displacement at all time is called the node, while this region over here where the crest is usually meant to be, or where the trough is usually meant to be, is called the antinode. Those are the principles for standing waves. Then there are a few kinds of standing waves they refer to in IB or there are a few kinds of standing waves that form. So the first one is standing waves on strings. So we'll just go through that. So we have the first harmonic, as it's called, which is where you have no nodes and one antinode, that's over here, n equals 1. Now in this case, let's say the length of this is equal to L. This length here is equal to L. So the wavelength of this wave is going to be equal to 2L over 1. And the frequency is going to be equal to the velocity over 2L. Now let's look into why this is the case. Now look at this part of the wave. It's just like this. Just like that. And if I draw this further, we get an exact same shape. Now that is a whole wavelength. And this length here, L, equals to this length over here, L, which means the wavelength will equal to L. And why does the frequency equal that? Well, we have V equals to F lambda. We know lambda equals to L, so V equals, sorry, so we have V equals to F times 2L, so therefore F will equal to V over 2L. Now let's look into the second harmonic, n equals 2, where now you have one node and two antinodes. So in case of a standing string, the harmonic is dependent upon the number of antinodes that are present. Over here, the wavelength is equal to L, or I'll just write it as 2L over 2 for now, so that I can show you a pattern at the end. And the frequency equals to V over L, or 2v over 2l. Alright, now that whole thing is one whole complete oscillation because you're going from one point through a trough, then a crest, and then a trough, and then back to the same point. So it's a complete oscillation. So this length is the wavelength. So equals to L. And the frequency is, well, speed over wavelength, so W over L. Now let's look into the third harmonic, n equals 3. We have 2 nodes over here and 3 antinodes. So those are your 3 antinodes over here. Now in this case, the wavelength is going to be 2 times the length over 3, and the frequency is going to be 3 times the speed over 2 times the length. Now let's look into why is that. So now this whole wave, let's draw it out, is equal to that. And this whole thing is the length. But the distance we're looking out for, that's L, length. This is what we're looking out for because that's from one point through a crest down to a trough and then back to the same point. This is 2/3 of the length, so the wavelength is 2/3 of the length. Now using this again, V equals to F times lambda, we get V equals to F times 2L over 3. So 3V equals to F times 2L. Therefore, F equals to 3V over 2L. Now looking at all of this, there's a clear pattern for the frequency and the wavelength of any harmonic. Let me just get rid of this at the side. Now we can come up with the relationship that in case of a standing wave, its wavelength will always be equal to 2L over n, where n is the harmonic number. And we can say the frequency equals to NV over 2L. You don't need to remember these exactly, but you should be able to find them out when in an exam. And the similar process is followed through in case of standing waves in a pipe with one end open or both ends open. Would you like me to go through that as well? Okay, Y squared, thank you very much for looking it up. So frequency is constant, while the wave speed and the wavelength will change proportionally when it refracts. Sorry if I'm super... Okay, so why does the n relate to the superposition? I'll just go through that quickly again. So if we have a wave, I'll just draw it a bit, a few oscillations. You draw that a bit better. Yep, if I have a wave like this, so we know that this is one wavelength, right? the distance from here to here. That is a wavelength. Now, actually, let me take a crest to make things a bit clearer. And draw some axes so I can give them values. Okay, so let's take the crest over here. X, O. So now, if there's a path difference of n times lambda, so any wavelength across, let's say one wavelength across, then you have the point over here, which is another crest because that's one wavelength. Or you have, if you have two lambda, which is two wavelengths across, you have another crest over here. Note, at any n times lambda path difference, you're always going to end up at another crest. And by the principle of superposition, the displacement values add up. So you end up with a bright spot, which is 2x0. They constructively interfere because both the values are positive. But however, if I'm half a wavelength across, or 1.5 wavelength across, and so on, then I end up at negative displacement. In this case, minus xo. Because of that, if there's a half or a 3/2 or a 5/2 path difference, the resultant wave will have a displacement of xo minus xo, which is 0, and that's destructive interference. How does this work for negative numbers when it's a bright one? Yep, it reflects on to the y as well. So if you have n equals -1, but we don't generally use negative numbers because if you remember, as I said earlier, when sorry, I went a little too far. So when we say n is going to be a whole number, so we don't really look into integers. So either the path difference is going to be 0 or it's going to be something greater than that. -1 will be the same as 1. Yeah, you could say we take the absolute value. So, is there any other question before I close down the session? How do we know do we need to know how to calculate the intensity for the bright spot? Well, you don't really need to know exactly how to calculate the intensity for the bright spot, but you may have to use the relationship to do it, because if you remember clearly, by the principle of superposition, the bright spot will have an amplitude of 2x. And you know that the intensity is proportional to the amplitude squared. So you can use that relationship to determine how much the intensity has changed by, but they'll never ask you to raw calculate the intensity. How much difference is there between n0 and n1? When you say how much difference, do you mean how much path difference? In that case, yes. Intensity difference gets a bit weird. You don't need to know that, so you can just skip on that. Okay, then I'll end the recording.